Okay, we don't have enough time in one 5-minute video to go over all 4 of these, but let's look at number 2. And by the way, there seems to be a typo here. Is that the sine of x? I have a feeling it is. But anyway, when we solve a differential equation using integrating factors, we want to work with an equation that looks something like this. Y prime, or dy dx, plus some function of x only times y equals some function of x. And so what we want to do is take this equation right here, the original, try to get it into this form. So I can see a y prime here. So if I divide every term by this x times the quantity x minus 1, turns out I get to this form, because this term becomes a y prime plus this term becomes y times this function of x. That's p of x right there. And this divided by x times x minus 1, we can cancel this factor of x out, which I do in the next step. That becomes an exponent of 2. And now we're ready to find the integrating factor, which is e to the antiderivative, or the indefinite integral, of p of x. And that's what p of x is, this expression right here. To get the integral of this exponent, I have to use partial fractions. So that's what I've done right here. I can write that the antiderivative minus 1 over x is minus ln of x. I left out the absolute value symbols. And then if I use properties of logarithms, I can write this as ln of x minus 1 over x. That's what we have here. And e to the ln of anything is the anything. So there's your integrating factor right there. So we want to multiply every term of this equation by the integrating factor x minus 1 over x. There it is, x minus 1 over x, x minus 1 over x, x minus 1 over x, and simplify on the right, and then take the antiderivative of both sides. And the whole point of using integrating factors is that the left-hand side is a result of using the product rule. And it's the product rule of the integrating factor times y. Go ahead and practice taking the derivative of the left-hand side, and you'll see that you end up with this, because you have the first function times the derivative of the second, that's this times y prime, plus the second function, y, times the derivative of the first. And if you take the derivative of the first, you'll see that you get what this thing simplifies to. These x minus 1s cancel out. You have 1 over x squared, and that is the derivative of this, 1 over x squared. So we have to find the antiderivative of x e to the minus x squared, which I've done over here. This is just simple u substitution. And we get minus 1/2 e to the minus x squared plus c. That's what this is. Now to get y by itself, I divide both sides by this integrating factor, or multiply both sides by the reciprocal of the integrating factor. And there's your answer right there. That's a general solution for the original differential equation. If I go to board 3, I can show you on Desmos how you could use Desmos to check your answer. There's the original function. I can put parentheses there. And if I use the Desmos derivative operator to say that g of x is the derivative, well, then here is the original solution, plus y prime times x times the quantity x minus 1. And here's the graph of the right-hand side of the differential equation, x cubed times e to the minus x squared. And they're the same graph. So these two are equal, and therefore this is a solution to this differential equation, where this equals this down here. Okay, hope that helped. If you want to repost problem number 3 with a correct, confirming that's the sine of x there, maybe I'll take a look. There you go. Hope that helped. And if you have any questions, post a comment.